with actually the first slide talk of this conference. Code CFTs, the optimal, the average, and the page master.
Thank you very much. The talk starts with a portion of public shame.
We respect your courage.
I made a mistake right on the title page because it's July, not June. Let me explain. I tried to give this talk as a Blackboard talk. I visited Slava like 2 months ago, and Slava insisted I give a Blackboard talk, and it didn't work out well, so I decided to experiment with the slides. The idea of this talk is to give some sort of overview of the things we have been doing with collaborators for the last 2 years. So I tried to pack a lot of things in a non-technical way. It's a non-technical talk. I consider it to be a review. And please ask me things. I will stop and try to explain things. But again, I'm not trying to convey things at a technical level. I don't think it will be possible. But my hope is to convey some sort of overall picture and to get some of you interested, all of you interested, and then we can go from there. So besides the first time in my life making a mistake just on the title slide, I also have a slide which says philosophy. I've never had that before. So that's perhaps the most important slide of this talk. As you see, it's completely non-technical. Now, this slide assumes certain background knowledge which you may not have, but I'll try to explain things, and then maybe toward the end of this talk, this slide will become more clear. So let me actually. So I have like one hour, right? And maybe if questions come, it will answer. But only if questions will fit. So the main picture, the main philosophy is the following. Everyone in this room is familiar with the task of trying to bootstrap conformal field theories. I will be thinking only about two-dimensional conformal field theories and modular bootstrap, and we can try to put constraints. It's a linear programming constraints, maybe more sophisticated constraints. We can try to put these constraints, for example, to maximize spectral gap. That's one of the conventional tasks. So we are familiar with that, but we all know that this is a very complicated problem, especially because we don't really have any good idea how the space of two-dimensional CFTs looks like. We can explore some very strange, very peculiar corners, but we don't even have a mathematical definition of what the space of all CFTs is, right? It's an abstraction. But then the point is, this story with Bootstrap, modular bootstrap of two-dimensional conformal field theories, it's actually a very sophisticated and complicated cousin of much more pedestrian discrete mathematics problems. When I say pedestrian, it means that it's very easy to explain what those problems are and define them rigorously. But of course, those problems are very complicated and have not been solved, despite decades of effort on by a community of mathematicians. So these are simpler cousins of the modular bootstrap problem. And I wanted to convey this point because I don't think it's very well appreciated by our community. That we are solving a more complicated version of what mathematicians have been solving for decades. So besides conformal field theories, there is this thing called codes. I'll try to explain what they are, but if you saw even one movie with computers and hackers, you know the codes is a sequence of zeros and ones which you use to send encrypted messages. And basically, it's a chapter of discrete mathematics, and therefore it's very simple at the level of definitions, at the level of basic properties. You just basically deal with like binary codes. These are just binary 0 and 1 matrices, something like that. Then there's also another very well-known problem, CR packing. You basically try to take oranges and pack them in the most optimal way. Just try to do it in higher dimensions. We know, thanks to Delimil and Leonardo and Tom, that this problem of CR packing is very closely related to conformal bootstrap. They establish a quantitative connection, but I want to emphasize that there are two things. There is quantitative connection and there is also qualitative similarity. So there is quantitative connection, and by the way, yesterday, Marina Gazovska, who solved the sphere packing in 8 dimensions, was awarded Fields Medal. So we all should be happy about this, because in retrospect, Dalimil's work and his collaborators is getting recognition and a wider community. So congratulations. Right. Thanks to that work by Dalimil, Tom, and Leonardo, we know that there's a quantitative connection between sphere packings and CFTs. A series of my works is an attempt to establish a similar quantitative link between conformal bootstrap and codes. And of course, in mathematics, people know for decades that there is quantitative link between sphere packings and codes. So all of these things are morally and quantitatively related. And so this is one point. But then also you can ask me, okay, so it's like a dictionary, not like ADS-CFT dictionary, because ADS-CFT dictionary is an equality. The left-hand side is equal to the right-hand side. Here it's like moral equality. But you can ask, well, let's establish a dictionary. If I try to maximize spectral gap, what that is on these other instances. Now, in the sphere packing case, we know what it is. It's an attempt to find the most dense packing. And in the code case, it's also completely standard mathematical problem of finding the best code. The best code is the one which encodes information the best. I'll try to explain what this means, but intuitively it's clear that different codes offer different level of security or encryption or density of packing of information. So we try to optimize that. Now this is at the moral level, but there's also quantitative level that you can try to do modular bootstrap, and this is a set of linear programming constraints. Similar linear programming constraints also exist in a case of sphere packing. They're called Cohen-Elkis conditions, linear programming, and Dalimil's work with Rostelli and Hartman establishes exact link. But also in case of codes, there is linear programming. I call it baby bootstrap, but I shouldn't call it baby bootstrap, because in mathematics since late 60s or 70s, they call it de la Sartre's linear programming. De la Sartre is a French mathematician who put forward a set of linear programming constraints. They're baby version of Bootstrap. Sometimes you can relate them to Bootstrap. And they're much simpler, still haven't been solved completely. That's an interesting thing. So one takeaway from this philosophy slide is that since in physics we usually, what we do when we cannot solve a problem, we try to solve different problem which has the same flavor but similar. So here is an option to have similar problem but certainly much simpler. And last point here at the philosophy level is that codes and sphere packings in fact come in ensembles. And Tom today was talking about ensembles of CFTs. It's difficult to define mathematically, but you can have working definition, but saying that you have statistics of OPE coefficients, that's related to gravity, but also you can have ensemble of codes, and that's a mathematical well-defined thing, because codes are discrete objects, so you can define what the ensemble of codes is. And also you can have ensemble of sphere packings. That's a little bit more complicated, but if you, for example, say that you will only put oranges in a lattice way, like a crystalline lattice way, then the ensemble of codes will be just an ensemble of lattices. It's a mathematically very simple thing to define. And I want to stress during my talk that these ensembles have qualitative similarity and perhaps quantitative similarity as well. So even if you want to study holography by averaging over CFTs, you can first try to do it, let's say, at the code level. So this is one of the takeaway messages from my talk. So that's philosophy. I probably spent like 50% of my time talking about it. Any questions about this? This is, okay. Yeah, everything is clear. Okay, before I start going into details, I also want to give you a little bit of history, because I don't want to explain everything from the first principles. I just want to talk about the most recent paper. But the history of this subject is only 2 years old, essentially. So there was an old paper 30 years ago when, first of all, let me ask, shall I explain what Narayan CFTs are? Everyone knows what Narayan CFTs are? I'll maybe just say the definition that in 2 dimensions you can very easily build a conformal field theory by defining a sigma model. That just fields going in some curved manifold. But there is a simplest version of the sigma model, and you have fields going in a multi-dimensional torus with a flat metric. It's a flat metric and a multi-dimensional torus, and you also have constant B field. So this kind of simplest model is a worldsheet CFT. It appears in the early instances of string theory, and corresponding CFTs, they form a family called Narayan family because Narayan studied those CFTs. And mathematically, those CFTs are parameterized by what is called Narayan lattices, and that will be important for us. So 30 years ago, this group of people noticed that if you start with classical codes, you can start building CFTs, which are not quite Narayan CFTs, but sort of the chiral version of that. So you can build chiral version of Narayan CFTs. And more recently, 2 years ago, with my collaborator Al, we realized that if you extend this and you start not with classical codes, but with quantum codes, then you can actually start with quantum codes of particular type and build Narayan CFTs of particular type. So we were very happy because quantum codes is in the center of attention. There may be some physical meaning to it. And later, a year ago, we realized that this construction is not unique. You don't get all Narayan CFTs this way. You just get some Narayan CFTs this way. But that's okay, because if you go back to the relation between codes and lattices, or codes and sphere packings, it's very well known. Codes is a simpler object, it's a discrete object, and sphere packing is a continuous object because you can move oranges continuously. So it's very well known from mathematics that if you start with codes, you can get some sphere packings, maybe even best ones. For example, the one in 8 dimensions, which was also proved to be the optimal, and of course people knew it's the optimal. It's based on E8 root lattice, but you can also start with a code. It's called the 8-4, I don't remember, 8,4,4 Hamming code, the perfect Hamming code. So you can start with a code and get certain lattices and certain packings. And here you start with the codes and you get certain Narayan CFTs. But then we realize you can extend that, but you extend it in a way that your codes are not really quantum. So we call it the bottom-up procedure, and you can extend it even further. And 3 months ago, there was a paper where people started from codes of different kind and also mapped them to CFTs. And a week ago, we had sort of like an umbrella result. We generalized all of these, this is for chiral, we generalized all of these into a family of constructions, which I will try to explain today. And it's an infinite series of constructions where you have different classical codes and you map them to very, very different Narayan CFTs. Why this is interesting? Because if you have this map, the interesting important properties of CFTs can be backtracked back to codes, and it's much easier to study them on the code side, because codes, I keep repeating, is a much simpler object. So it's basically a vehicle or a tool to simplify many problems. So I will try to explain this work today, and maybe some takeaway messages. But before I do that, I probably need to start explaining what code is. So I gave you a real-life example, the alphabetic code. Now, if you try to spell your name over a phone, over a noisy channel, instead of each letter, you start using pre-described words. Some smart person pre-described these words, and those words are pre-described in a very simple way. Those words should sound as different from each other, as distinct from each other as possible. This is intuitively very clear. If you speak over a noisy channel and you have code words which sound very similar to each other, you will not achieve your goal of spelling things clearly, right? So this is an intuitive example, but the takeaway here is the following. A good code, so this is a message, this is a code word. This is a code word. The takeaway lesson here is that a good code is the one where code words are as different as possible. But at the same time, we want to keep the number of these code words large, otherwise you will not be able to convey anything interesting. Or you will have to repeat things many times, like in a Morse code. Morse code, yeah, you have. Good. What is the formal mathematical definition? These are classical codes over some group G. So I will start with some abstract abelian group G. And elements of this group G, call them the alphabet. and then I will have a string of letters from this alphabet that I will call the code word, or you can think of it as a vector with the values being elements of this group. And then a collection of these vectors, any collection of these vectors you can call a code. Any collection of these vectors you can call a code. That's up to you. You have certain number of code words, that's it, that's the code. Okay? Now, again, if you try to use this code for practical purposes to send information using this code, you better make these code words as distinct as possible. And at the same time, keep the number of code words as large as possible. Today, I will be only talking about a special family of codes called the additive codes. Additive codes is when you say, you know what, I want the code, which is a collection of code words, to have the following property. Any linear combination of a code word better be a code word. I impose that by hands. That's my definition. That's for since this is an element of an abelian group, then what A1 plus A2 is a well-defined thing. So basically, with this definition, a code becomes a vector space because things are closed under addition. It's a vector space which is a subspace of G to the power n. It's a discrete vector space because you're only allowed to multiply things by integer numbers, and the total number of elements here is finite. It's the size of the alphabet. It's the cardinality of the group G to the power n. It's a discrete space. So you have something which is not usual in our community. You have a discrete linear space which has only finite number of elements. But in mathematics, if you work over finite fields, that's what happens all the time. Now you can make things more complicated and equip you can equip the group with a scalar product. Once you equip the group with a scalar product, you can extend the scalar product to this whole space. And once you extend it to the whole space, then you can define dual spaces. Dual spaces are orthogonal. The space dual to a given one is the space orthogonal to a given one. Now, in the conventional Euclidean space, orthogonal means that the scalar product is 0. But in this case, it also means 0, but the following thing happens. The vector could be self-orthogonal. So maybe I can give you an example. When did I start? I just want to keep track of time just a little bit.
I think it was at 11:20.
11:20 I started? Okay. So one example of our classical linear codes or classical binary linear codes. In this case, linear and additive is a synonyms. I will not explain what the difference between them. So you basically say that your code words are either zeros or ones. So if you want to have vector space, you always must have 0 vector. And let's consider two-dimensional, n equal 2. And then you can have something like this. And this code is self-orthogonal, and in mathematics called self-dual. Because any vector here is self-orthogonal. How to see that? It multiplies C1 by itself. You have 1 plus 1 equal 2. But then you need to work mod 2. You need to work mod 2. That's how we define things in the binary case. And then it becomes self-orthogonal. So if you're working with the binary codes, there is a notion of self-orthogonality of a vector. Then there's a notion of self-orthogonality of a code. And this code is called self-dual. That's the simplest example. Okay, so that's one thing I wanted to say. And another thing I wanted to say, if you want to visualize a binary code, let's consider now a more abstract binary code which has 0 element and some other element. There are many elements. There is 2 to the k elements because you can add them in different ways, in different pairs, so it will be power of 2. And let's say the length of this is n, but each element of this vector is 0, 1. Geometrically, it means the following, that each code word, each vector denotes a vertex on a unit cube. You have a multidimensional unit cube. Let me try to draw it. You have a multidimensional unit cube, and each code word is a vertex on a unit cube. So then the question of having a good code is a very simple one, at least visually. You have a unit cube in n-dimensional space, let's say 10-dimensional space. you want to choose vertices of a unit cube such that the distance between them is as large as possible. It sounds a completely trivial thing if you have 3-dimensional cube, but if you have 72-dimensional cube, nobody knows how to choose those vertices such that distance between them will be very large if you specify the number of vertices. So let's say n equals 72, and you want to choose 2 to 72 over 2 vertices. That's a big number. It's not a random number. I take n over 2 because a self-dual code will necessarily have that many code words. So you want to choose this number of vertices while keeping distance between them maximal possible. Nobody knows how to do it. Nobody knows what the distance will be. Okay, so it sounds like a completely trivial problem, much simpler than conformal bootstrap. And I'll try to explain it that it has flavor of conformal bootstrap because basically maximizing the distance between these points is maximizing the spectral depth. Okay, so now the general construction. These are the only few technical slides I have. So the general construction is the following. Let's start with a 2-dimensional space, and it will be a Minkowskian space. It will be a space with a metric 1, 1. And I want to define some lattice lambda, 2-dimensional lattice lambda, simple object. But I want this lattice to be even and integral. What does it mean, even and integral? Even means that the square length of any vector belonging to a lattice, I want it to be an even integer number. Not just a number, but an even integer number. And the scalar product of any vector from the lattice with any other vector from the lattice, I want it to be an integer number. No, not necessarily even, but an integer number. This requirement of integrality might be unnecessary once you say even here, because this might follow from here, but I say it for completeness. Integrality means that you can define a dual lattice. Dual lattice, that's a conventional, what's a Minkowski 2-dimensional space, but for simplicity you can think about Euclidean 2-dimensional space. And dual lattice, well, we all know what it is. If your 2-dimensional lattice is a crystalline lattice of some graphene, then the dual lattice is a lattice of momentum, right? If the dual lattice is a lattice of, yeah. So it means, for integrality, it means that the lattice should be a sublattice of its dual. All right, so that's a mathematical starting point. I demand that. Now, all of these lattices are very easy to classify because integrality means that the scalar product, the quadratic form defined by the lattice, that's basically the quadratic form of the vectors. It has to be integer valued, and it should have integer numbers, even numbers on the diagonal. That's the most general 2x2 matrix, which is integer valued, but even numbers on the diagonal. It's parameterized by 3 numbers, right? No, these 3 numbers are not unique. There could be equivalence condition. People understand how this equivalence condition between these triples works. But in general, there is an infinite series of this quadratic form, hyperbolic quadratic forms. Once you have a hyperbolic quadratic form, which is parameterized by this triple, we can define what is called a glue group. A glue is just a name, but let's call it a group. And that's a quotient of a dual lattice with respect to conventional lattice. Lattice by itself is an abelian group. It's a bunch of vectors which you can add to each other, so it's an abelian group. So a quotient of an abelian group will be an abelian group. It will be finite dimensional, and it will be Zp over Zq, sum Zp over Zq. That's the only thing which could be there. P multiplied by Q is a cardinality of the group, and that's very easy to understand from the determinant of this matrix. So P multiplied by Q will be determinant of this matrix with a minus sign. And P can be defined as the greatest, well, it cannot be defined. P is equal, it's not a definition, it's a result. P is the greatest common divisor of all of these 3 numbers. And Q is the rest. Okay? So basically you start with a 2-dimensional lattice, you define a group. That's exactly the group which will appear in the definition of a code. And then, since our lattice was living in a 2-dimensional space with the Lorentzian metric, you can inherit this metric or the scalar product and bring it back on lambda perpendicular, and then bring it back to G. So you will have an abelian group, Zp cross Zq, equipped with a scalar product. I'm not writing things explicitly, it's clear that we can write them explicitly, but I'm skipping all of these technical details. Now, okay, you have a scalar product which is inherited from the Lorentzian metric into dimensional space. There is one subtlety. If I only deal with Lorentzian structure, the only thing I can write is this one. That's a completely universal result. I only have 3 numbers, or rather triples up to equivalence condition. And they parameterize all Lorentzian integer lattices this way. All Lorentzian even lattices this way. But in reality, besides Lorentzian structure, very soon I will need Euclidean structure. I will want to calculate Lorentzian scalar products of vectors. I will want to calculate Euclidean scalar product of vectors. So I can, of course, introduce Euclidean scalar product to be like plus signature. But then I have a symmetry group, which is a symmetry of Lorentzian structure, but it's not a symmetry of a Euclidean group, right? And this group will generate different Euclidean matrices starting from this lambda. So each lambda, you should bear in mind that each lambda gives rise to one parametric family of different Euclidean lattices, which are equivalent as Lorentzian lattices. So my construction is parameterized by the following parameters: triple M, M, and K up to equivalence conditions, which I'm not writing, but you can look them in the paper. Triple M, M, and K, integer numbers, and the one parameter from O1, 1. It's a continuous parameter. The rest is completely straightforward. Now, I can imagine I have a code. So first I have a group. I take this group to the power C. I used to call the length of the vector n. I don't call it n anymore because n now is playing the role of n, m, and k parameters of this lambda. Now I call the length of the vector c. What is the c? That's a central charge of an Orion field. So I'm sort of preparing the dictionary. I take this glue group to the power c. That's a vector space. I take a subvector space in this vector space and call it a code. And then the following is true. If I have a code, I can build a lattice using this code. And this lattice related to the code, it will have the following property. It will have this lattice as a sublattice, and it will always be embedded in this lattice. So I have this glue lattices C times together, that's always a sublattice, and the dual glue lattices glued together, that's always where my lattice lives. Shall I make a picture of some sort? You can think of it as the following. Let's think lambda. Let's think lambda would be a square lattice, and we will forget about Lorentzian structure. That's easy to do. So if lambda is a square lattice of some particular size r, then the dual one will be 1 over r. So you want integrality, which means that 1 over r will be divisible by r, or the other way around. I don't fully understand it now. So it means that r squared will be a rational number. So that already smells like a boson at the compact rational radius. That's where we're going with this. But basically, maybe I should make this example here. Let's even make simpler case. Lambda is one-dimensional. One-dimensional lattice is something very, very simple. And then let's do the dual lattice. That will be 1 over r, 2 over r, and so on and so forth. I want lambda to be a sublattice of lambda bar, lambda perpendicular, or lambda dual, correct? Language is lambda dual. So it means that 1 over r should be divisible by r, right? And that basically means that you can have somewhere here, let's say, is 1 over r. So this is your dual lattice. This is lambda perpendicular, and this is lambda. And your lattice will be somewhere in between. I'm probably, yeah, I'm actually making things completely opposite. That's how they should be. If lambda perpendicular should include it, means that 1 over r should be small. I messed up with this picture. It's a bad thing, but I will redo it. It's only one-dimensional lattice, so it's, after some trial and error, I'll get it right. And then R is somewhere here. So this is lambda dual, this is lambda, and your lattice, our code lattice, will be somewhere in the middle. For example, it could be something like this. But also, it will divide this. Okay? So this is sort of a high dimensional generalization. And then started, that was just a property, that's not a definition. What is the definition? The definition of this lattice is the following. You take all the vectors in this lattice, all the vectors in this lattice, and you look at them, and some of them you will keep, and some of them you will throw out. And the resultant thing will be a lattice. It will have less vectors, but it will still have enough vectors, and there will be a linear structure, so it will be less. And the rule to keep vectors is the following. You look at this vector, you take a quotient of that vector with respect to this, and this quotient necessarily will be a group element, or rather a group element to the power c. And if this bunch of group elements is an element of a code, that vector you keep. All other vectors you throw away. Okay? So in mathematics it's called construction A. It's a completely trivial thing. That's the formula. So the punchline here is that you give me a code, I give you a lattice. That's perhaps not very illuminating, but the following thing is important. If I start with a code of a particular type, or which has particular properties, my lattice will also have very nice properties. In particular, if I say that my code is even and self-dual with respect to the scalar product which was inherited from the lattice, it means that the corresponding lattice will be even and self-dual with respect to the scalar product, which is just a sum of Lorentzian scalar products. So this is a cheap way to produce even self-dual lattices in the space R, C, C, the Lorentzian space with Lorentzian signature. For that, you simply need to generate even self-dual codes. Yes.
Is it fair to say that this code becomes more or less like the unit cell of the lattice?
It's exactly right, and I used to give talks when I literally would do that. You have a unit cell of like, exactly. I used to have this, right? So we already know that in binary case, a code is a bunch of points here. So you need to actually move them in a parallel fashion with a step 2. Like you don't do this and copy it right here. You copy it with a step 2. Otherwise it will not be periodic in the right way. But you copy it in a step 2 for the binary code. For the code which are more complicated, the pattern is more complicated. But the idea is to take a unit cell and put it in a parallel fashion. This formula simply tells you that if you have a vector somewhere, to understand whether this vector belongs to a lattice, you sort of move it parallel to the unit cell, and if it becomes one of the highlighted points, which means it's a code word, then you keep it, and otherwise you throw it away. So thank you, Joao, that this is the right way to think about it. Okay, so to generate even self-dual codes, it's an algebraic task. If your C is small, you can do it on a computer by trial and error. In general, you can usually calculate how many codes you have, but again, we don't know all of them, we don't know the best of them. The space of them is mathematically well defined, but still quite complicated because the number of codes is growing exponentially with C, with the size of the vector, with the size of the code. But nevertheless, we can generate codes, at least conceptually, and produce even self-dual lattices, which will give us immediately Narayan theories. And then, up to some subtlety, which I don't want to spend time on, but up to some subtlety, you can ask, what's the spectral gap of my Narayan CFT? And I'm talking about spectral gap of U1 to the 1, U1 to the C cross U1 to the C primaries. That's exactly characteristic of a code which is called Hamming distance, or better, I should call it generalized Hamming distance. In simplest case, that's simply the minimal distance between code words, the highlighted vertices of unit cube. So if you manage to put points on a unit cube such that the distance between them is very, very large, in retrospect it means that you managed to construct a CFT with a very large spectral gap, and that's exactly what we want, right? That's exactly what we want. So the formula is something like this. The spectral gap is just the Hamming distance divided by 2, so it's a completely trivial thing. Okay, so just to complete this general introduction, I need to explain what's the mileage of constructing CFTs from codes besides spectral gap, or maybe just to give you the full picture. The real thing is that when we have a CFT, we quite often want to calculate the partition function. Let's say the torus partition function. And for a general CFT, that's a complicated thing. And even for an Orion CFT, we usually don't know how to do it besides just writing an abstract sum over all lattice points. But if you started with a code, then there is a way to do it in a much better way. Each code can be associated a polynomial, just an algebraic polynomial, which depends on a bunch of variables. A and B are, yeah, I forgot to write this. A comma B is an element in the group G, which is ZP cross ZQ, which means that A goes from 0 to P minus 1, and B goes from 0 to Q minus 1. So basically we have PQ variables here, and I want to define a polynomial, which is a homogeneous polynomial of PQ variables, and I do it like that. I go in a sum over all code words. Each code word is a collection of group elements, and for each group element I simply have a product of variables where each variable corresponds to a particular group element. So it's a completely trivial definition. I have a homogeneous polynomial, but, and this is somewhat non-trivial, if your code was satisfying certain properties such that evenness and self-duality, it means that this polynomial will be invariant under two particular specific linear transformations of this variable psi. I'll give a more explicit formula related to this original construction we invented 2 years ago, later in the talk. Here we give everything explicitly in our recent paper, but I don't want to write it here because the formulas are rather complicated. S transformation in a second will be S transformation of SL to Z, but at the level of this psi, it will look like discrete Fourier transform. So it's a rather involved formula. Now you define this polynomial, which satisfies two particular algebraic relations. And if you want to, you can try to sort of solve this algebraic relations and find the ring of polynomials, ring of all polynomials which satisfy these algebraic relations. In many cases, this is a practicable, doable task. Once you have this polynomial and you want to obtain the CFT partition function, you simply stick instead of this polynomial, instead of these variables, certain functions which are essentially two-dimensional generalizations of Jacobi theta functions. Each of these functions is parameterized by group elements, but you sum here essentially over two-dimensional lattice. Jacobi theta function is a sum of one-dimensional lattice like this, and here we have a two-dimensional generalization. So these functions, they satisfy certain algebraic identities under S duality, under S and T transformations of SL to Z. They depend on torus parameter here, omega. So let me explain here. Omega is a very simple 2x2 matrix, which is explicitly made out of tau and tau bar. It's universal. It's something like tau 2, tau 1, tau 1, tau 2, something like that. It's a very simple matrix. V is a vector in two-dimensional lattice, which is congruent to a group element which you started with. So basically it's a very straightforward expression. But once you start applying SL to Z transformation on tau and tau bar, these psi's will go into each other exactly as variables here under which your polynomial was invariant. And that will ensure that your CFT torus partition function is modular invariant. And there is a generalization to higher genus. Johan and Brian and my student Ashish during last year generalized all of this for the original construction to higher genus. So they have written more complicated expressions, and then you have higher genus. I think genus 2 and genus 3. Yeah, okay. Genus 2 and genus 3 partition functions for this code CFT. So if you want, you can go to higher genus. So now the benefit is clear because you can very easily calculate modular invariant CFT partition function just starting from the code data. And the key is this polynomial. And polynomial is a much simpler object to deal with than the full CFT partition function.
Sorry, just to be sure, in the first definition of the polynomial, psi is just the variable the polynomial depends on.
A set of abstract PQ variables.
Labeled by all the elements of the code.
Labeled by the group elements. There are as many variables here, abstract variables, as there is group, the size of the group.
Oh, okay.
Okay. Now, this is a detour slide. I will just spend 1 minute on it because my the setup is there. I already finished the setup. I already gave you all the important. Yes.
Sorry, just to understand the previous slide. So this is some particular Lorraine CFT of C, with C, the central charge C.
Well, this is a general construction which gives you an infinite family of different code types.
It's a discrete family. It's not any Lorraine CFT.
It's an infinite discrete family of different code types. For each code type, you can have, and given C, you can have certain number of codes, and then you produce many different Narayan CFTs, but certainly not all. It might be that eventually you will get a dense description. We will maybe talk about that in 5 minutes.
Where did like P and Q go in terms of the Lorraine CFT? There was a P and a Q.
Yeah. I mean, it's right. It's not a trivial question because I didn't study all of these infinite families in detail, but I know a particular subfamily. So there was a paper 3 months ago, and they proposed a construction with ZP cross ZP, and that's a part of this construction as well. It's a particular family it's a particular infinite series out of many more infinite series. So this family corresponds to an Orion CFT, which is a compactification on a cube of size square root of p, or maybe 1 over square root of p, I don't remember exactly. So the torus is the cube of this size, and then you have all possible B fields. Oh, you have all possible B fields which are quantized in terms of P. So it's not all possible continuous B fields, but some quantization in terms of B fields, what B fields could be equal to. Now, it's not a dense set within all Narayan families, but as C increases, there is a chance that we will get to something dense. I don't know if that's true, but I have a reason to believe that might be true, and I will explain it in
Are these Narayan CFTs with enhanced symmetry? Because like
Some of them-
standard one, you can't just write the Narayan partition function as a polynomial and theta function.
And these are more complicated theta functions. They're like two-dimensional. They're not Jacobi theta functions. Obviously, if you have general point in the Narayan moduli space, this description will not work. Whether they have enhanced symmetries, I don't think so. Some of them probably do. In the general case, I don't think so. But of course, this is not the most general Narayan CFT. The same way how starting from codes, you will never get all possible sphere packings, but you might get interesting, densest sphere packings. And that's where I'm heading with this story as well. Okay. A quick detour, the construction I presented, it's sort of bottom-up construction. You start with codes which you better call classical codes, and just map them to Narayan CFTs just because you can. There is no physical picture behind it, just an algebraic construction. You start with code, you build a CFT, you use the code to study. Mathematically, completely legitimate, but I'm not claiming there is any deep physical picture behind it. But our original paper somehow used quantum codes, and since they're quantum codes, you hope there might be some interesting physical picture behind it.
What is a quantum code?
I will not explain what that is, because in this day and age, everyone should know what quantum code is. It's a part of quantum information science, which is used in quantum computing. These words don't ring a bell. As some people say, everything is written in my paper. But okay, so what I was saying so far was bottom-up construction, but there is a hope to have top-down construction. Top-down means that quantum codes really have some physical meaning. So it's a completely perpendicular direction, but I also wanted to mention it. We had a paper like 6 months ago, when we really tried to see what's the role of these quantum codes. This construction is sort of orthogonal. I'm not claiming it's a part of any of the constructions I presented so far, But in this case, we managed to sort of give interpretation of quantum code and qubit Hilbert space in terms of CFT Hilbert space. And it, in some interesting twists that happen to be related to defect operators and stuff like that, and extended form symmetries and other stuff I barely understand. So this is just maybe an appetizer. This is just to get you interested. There is a hope that quantum codes could have legitimate role in all of this story, but it's not fully understood. So now let me proceed. I give you the general bottom-up construction. So let's now reap some benefits. First benefit, optimal. Remember there are three: optimal, average, repair. First is optimal. Optimal means the following. In Bootstrap, in the context of Bootstrap, we often want to find CFTs which maximize the spectral gap. So the question is, if codes could be of any help. I argue that perhaps they can, and one observation we have is the following. If you start with first 8 cases of what is optimal Narayan CFT? Optimal is my definition, which I just took from the language of codes. Optimal means that I maximize spectral gap. If you look in the paper by I probably mispronounced Afghani Jedi.
Good one.
How badly did it?
That's close enough.
Oh, okay. Yeah, I'll just refer to it as your paper, okay? Your uncollaborated paper. It's a very nice paper, which is very comprehensive, and one result there is that a conjecture of optimal Narayan CFTs, CFTs which maximize spectral gap, for central charges 1, 2, 3, 4, 5, 6, 7, and 8. First 8 cases. So what we did is that we went through all of these 8 cases and we identified all of these 8 theories of code CFTs. There's a different codes in different constructions. SQL one, it's a trivial case for some reason, which I don't want to explain, technical reason. We don't really have to, okay, I'll explain what the reason is. Remember we had O1, continuous parameter. It's very clear that if you're working with SQL 1, the only theory you have is the compact boson of radius r. And if you allow yourself to tune that continuous parameter, you can have any SQL 1 Narayan CFT you want. Therefore, obtaining optimal theory from codes is a mathematical triviality, nothing interesting there. But then if you go SQL 2, it's a special theory. This is called Z3 triality, Z3 invariant point in the moduli space. And you can obtain it from codes, but in a rather non-trivial way. You have group G, which is Z2 cross Z6, nothing nice. And the code is rather ugly, but it's a self-dual even code, and you obtain exactly the optimal theory. And then 3, 4, 5, that's an original construction of 2 years ago. You have this optimal theories. 6, 7, that's a construction. Another construction for the years from a year ago. You have optimal theories. SQL 8, it's a Barnes-Wall lattice. You also, it's not a surprise, you can relate it to codes. Barnes-Wall is a very famous lattice. There was all the reasons to believe you can relate it to codes. The code is nice. It's a code over Z4 cross Z4. The punchline here is that all of these nice theories which maximize spectral gap are related to codes. Obviously, I want to jump to conjecture and say that this pattern will continue. I don't expect to understand the pattern here exactly the same way how you will look at the densest sphere packings in 1, 2, 3, 4, and blah, blah, blah dimensions. Sometimes people know how to relate it to codes, for example, in 8 dimensions. And in other dimensions, they don't, or they know, but there is no beautiful or simple pattern. So I'm not advocating that there is a pattern here. All I'm saying is that, and that's my point, is that this optimal CFTs happen to be code CFTs, so it probably means that I can just look for optimal CFTs only among code CFTs. And that can give an opportunity to sort of create an alternative program of meta bootstrap. I already created the word before I actually implemented the program. And the idea is that I will be looking for theories with largest spectral gap only among code theories. Basically, I will be trying to find best codes of a given length. That's a difficult task by itself, because if C is sufficiently large, nobody knows how to find the best code possible. Of course, if C is moderate, 10, then perhaps you can do it. Sometimes you can do it brute force, Although here for SQL 10, there are exponentially many codes and you cannot go through all of them. Besides, there is another complication. There is infinite number of constructions. You can throw away some of them, and I have a reason to believe, which is related to this Del Sartre linear programming, that there might be a way to throw away infinite number of constructions such that only finite number of constructions will survive among the candidates for the best theory. But so I discussed that in the discussion section of this paper. That's a research question. I hope that there is a way to identify only certain, for given C, identify only finite number of constructions which give you promise to produce best possible Narayan CFT. And then the question of finding corresponding code and finding corresponding CFT will become a discrete optimization problem. Complicated one, but mathematical well defined. I do not know how, well, this is something we can make progress, we can hope to make progress. I do not know how to solve this optimization problem. With my students, I was playing with the quantum simulators, which give a promise of solving discrete optimization problem efficiently. So far, the capability of quantum platforms is lagging behind conformal bootstrap, but they promise a revolutionary improvement in the future. So one day, we might be able to use quantum computers to find optimal CFTs. So that's one part of the story. Okay, any questions about it? At least conceptually, it's clear what I was trying to say. We narrow the search only to code theories, and I have a reason to believe now that the best solution will be among those code theories. Okay, second instance, the average. I only have one slide, but I have to give you a lot of sort of intuition on this slide. So this is a completely different story. It's a story about ensemble of codes which will qualitatively behave similarly to perhaps ensemble of CFTs. The ensemble of Narayan CFTs is a well-defined notion. It's a continuous family. It's a manifold. It's a group manifold up to some factorizations, and you can actually average over ensemble of all Narayan CFTs. So we are very lucky in this case because we know what the ensemble of CFTs is. But I will try to argue that codes provide a cheap way to achieve similar behavior and sometimes even get quantitative insights. So there are a few different things. One thing is that the business of averaging over ensembles is not new, neither in discrete mathematics nor in physics. In discrete mathematics, averaging over an ensemble is a very standard way to put a lower bound on the property of the best representative of the ensemble. Let's say I have codes of particular type, and I want to know what's the best code, what's the Hamming distance, the property I'm interested in, what's the Hamming distance, the best Hamming distance of a code. Usually we don't know. But if I manage to average over all code and I calculate average value, then I know that the best value is better than the average value. That's a mathematical triviality. Also, it's mathematical triviality. That's one of the few methods people know how you can really say something tangible about best possible behavior of code. And in the code business, in the context of codes, this technique called Gilbert-Vershamov and corresponding lower bound on the distance, minimal distance between those points, called Gilbert-Vershamov bound. In the context of sphere packings, which are based on lattice, you also average over all lattices, and you get the lower bound on sphere packing, and it has the name of Minkowski bound. And more recently, people did the same with the Narayan CFT. They, in your paper, I refer to it this way, and they average over a moduli space over all Narayan CFTs, and they found the average spectral gap to be C divided by 2 pi e. That's an asymptotic value. And therefore, we know that the best spectral gap cannot be less than that. So I will refer to it as a Fami-Jetty bound, which is completely analogous in a mathematical sense to Gilbert-Vershamov and Minkowski bounds. It's the same mathematical idea. You average over all of them. Next step is a little bit non-trivial. Now I want to use similarity in structure, which nobody told me it is, but I conjecture it is, between codes and sphere packets and CFTs. And in case of codes, although people don't know for sure, but there is some evidence that the ensemble of codes is very sharply picked near mean value. And therefore, some people propose the conjecture that the average value is the best, asymptotically the best possible value. So we know mathematically, and there is a reason to see that you have a distribution which is very, very sharply picked. Just think about a Gaussian, which is a very, very narrow Gaussian. We will not even discuss what kind of quantity we talk about. You have very, very sharp Gaussian. The mean value will essentially become the best value, but only if you don't have tails. Statistically, people don't know how to control those tails. They don't know. Even in the code business, they don't know. But there is a legitimate belief, a conjecture among mathematicians. Some mathematicians hold by that conjecture, others don't, but it's a legitimate point of view. It's not that was proven wrong or something like that. That the best possible Hamming distance asymptotically is the average one. A little bit over a year ago, we proposed that some similar behavior will also happen with the Narayan CFTs. Now, for this to be true, the distribution of Narayan CFTs should be very sharply picked. And we were trying to clarify that by calculating something like variance. And we have shown that the variance is... We did the calculation for the codes, again, using the similarity. And we said that the variance will be exponentially small. And later, Scott Collier with Alex Maloney did the genuine calculation in the Narayan CFT case and obtained exactly the same result. So this is a consistency condition which gives you the picture that the distribution is very, very sharply picked. And it's not a crazy idea to think that asymptotically the average value is the best value. But nobody knows how to control possible outliers, so it remains a conjecture. So, okay, for a year and a half, we have a conjecture that this average value is the best possible value. The question is, let's assume it's the best possible value for the sake of argument. And keep in mind that it is for sure the average value. The question is the following. If I like code so much, can I really produce code CFTs with this behavior of spectral gap? At first, it looks completely impossible. Because if I start with this construction and start putting this cubes with a size 2, it means that this point will have an avatar at a fixed distance away from the origin. Or mathematically, if you remember, my lattice lambda c always included lattice lambda. And lattice lambda has fixed vectors of fixed size. It doesn't matter how large my spectral gap is, how many copies of this lattice I have. Once I have lattice like this, it includes vectors, and the length of these vectors don't grow with the central charge. It's a completely obvious obstacle, which people know already from the story of sphere packing, that it looks like codes is a horrible idea to produce large spectral gap CFTs. But since I have an infinite number of constructions, I can do sort of double scaling limit. I can increase my central charge and simultaneously adjust the construction. And if I start with this simplest construction, which is like square construction, ZP cross ZP, and if I adjust my P to be of order C or larger, and average over all code theories of this kind, the average spectral gap also happens to be this. So equivalence of average and of spectral gap here and here gives me an idea that maybe what Tom was asking me about, whether this code CFTs are dense, that might be true. I do not know if it is true, but I know that average, so I have a continuous moduli space, Narayan moduli space, and I average over all of it, and I have average value. And I know that I have discrete family, and I average over it. I have exactly the same average value. Of course, it doesn't mean that this set is dense within that set.
Sorry, so in this second paper, this is the average over Narayan CFT continuous family? Or?
This is a continuous result.
Okay.
And this is a discrete code CFT result. Okay? All right, I will not speculate about family being dense. I think that's a question which can and should be explored by someone. It's a straightforward question. But what I want to stress is the following. If you believe that asymptotically that's the best spectral gap, it means that cold CFTs can produce it, at least asymptotically. And that also adds value to my idea that if you're looking at the large spectral gap, all you need is cold CFTs. Okay, that was it. Yes?
So how did you pick that value of P? Was that tuned to get the answer?
If you take it smaller, then it will limit the size of the spectral gap. Because, as I said, you always have vectors of this original lattice lambda, and that limits the size of the spectral gap, so you want vectors of this lattice to be very, very long. If they are longer than something, then they are good, but they're shorter than something, that will be an obstacle.
So why not make it even bigger?
Yeah, there is no constraint here. You can make it as large as you want. You can make it as large as you want, but that already sounds suspicious. So I actually think that if you take it very, very, very large, it might be.
You still get C over 2 pi E if you take it.
By averaging, you still get it. By averaging, you still get it. But there might be some drawbacks which I don't fully understand in the ensemble of codes, how the distribution will look like.
But this average over codes is totally fixed P.
Yes, yes, yes. You fix P to be at least like this, and then you average over all codes of this particular family. It's a finite number. The way how you average, you basically find average enumerator. But each code has a numerator polynomial. You average over all codes, you find a numerator polynomial. You calculate average partition function, and that gives you the spectral gap. So that's the beginning. I kind of ran out of time, but maybe I need 1 minute more. Really not much.
Can I ask a question about
Yes.
how, if you increase this speed, how does the number of your code CFTs shrink?
It actually increases because as P increases, the size of the alphabet is P squared, and the number of codes grows with that. Last thing, and it's a very, I will not go into details, but last thing is the following. What else I can use codes for in the context of Bootstrap? And the idea is very simple. I can actually use codes to show that Bootstrap is not infinitely powerful. It used to be the belief that if you start with the Bootstrap equations and you solve them, then the solution is a genuine CFT. One beautiful example was on Monday in the context of a matrix model, where there was a bunch of Bootstrap constraints and then converged to the unique solution for a reason I still cannot fully understand. It's a miracle. And it used to be that whenever you solve modular Bootstrap, the solution always is a genuine CFT. I want to show it doesn't have, logically we know it doesn't have to be like that. I want to show it is not like that. The way to do it, I will be very fast. I will skip technical details, but the idea is the following. Remember that codes give us polynomials with particular algebraic symmetries. This is a particular algebraic symmetry in the original construction. In reality, I can construct codes which satisfy these symmetries, even though these codes are not related to any. I can write a polynomial which satisfies this symmetry, although the polynomial is not related to any code. And on the next slide, I will give you an example. Once I have a polynomial which satisfies this symmetry, and I plot particular Jacobi theta functions, I have a modular invariant object which looks exactly like a CFT partition function, especially if the coefficients of this polynomial are positive in integer values. There is no obvious way to say what's wrong with this ZC. But if I don't start with the code, if I give you a polynomial which is not related to code, then I don't have a CFT to associate with this object. So there are 6 polynomials. I forgot to write them. Okay, I forgot to write. There are 6 polynomials. They're not very complicated. It's a homogeneous degree 3 polynomials. I'm sorry, I forgot this slide. And we identified them 2 years ago. And the question was, those 6 would-be partition functions, do they relate to any CFT or not? At this point, codes don't help. You simply have an ansatz to solve conformal modular Bootstrap, and we have 6 solutions, and we wanted to understand if those solutions are genuine or not. So together with the collaborator from Weizmann Institute, we were looking at those polynomials very carefully, and we concluded that at least 4 of them are not corresponding to any genuine CFT. And the way we did it, one way was to show that they're not related to Narayan CFTs, because with the Narayan CFT you can count all lattices. I don't want to go into this because I run out of time. And a more general argument, which is also very specific to this particular Z we have, is that you have the Z, you expand it, you find an additional number of chiral vectors. Since you have a certain number of chiral vectors, 7 conserved vectors, and you have very small central charge, that gives you sort of a constraint on Cosmode algebra. It's a very particular case. It's not a general situation. It's a very particular hypothetical Cosmode algebra. Then you look through all possible representations of Cosmode algebra and see that all of them require additional states on top of what is written here. And that's how you conclude that this particular Z is not physical. It's not physical. Also, it's smaller invariant, and it's a decomposition into conformal, into characters, and so on and so forth. So in that case, codes simply work as a mathematical tool to give you an example of a solution of modular bootstrap, which is not a genuine thing. Something which we knew could happen, and finally happened. Okay, I'm done. There are conclusions. Let's just finish here. Thank you.
Do you expect that you can get a bigger gap in C over IE with the imposter Z's?
No.
No.
No,
So you think modular bootstrap would be enough for C over IE, and just take the imposter guy would still have a smaller gap?
well, this particular imposter guys we have are very small, but they have very small spectral gap. I think the question. I think the question you're asking is the following. So, yeah, people want to leave. I understand.
Okay, we only have this one.
In the context of Bootstrap, there is a very clear question. You solve the Bootstrap constraint, the best possible spectral gap. But your set of Bootstrap constraints, let's say spinless Bootstrap, is not the full set of physical constraints. So the solution you get is a genuine CFT on it. But the spinless Bootstrap, we know, is not a genuine CFT, right? That's from the papers, Beton. But the same thing is actually a valid question in case of codes. The Sartre's linear programming bound is literally the linear programming bound on these polynomials which satisfy symmetry. People know some constraints of those polynomials, but they don't have full understanding whether best possible polynomials, whether they would correspond to codes or not. So there might be a situation that you have polynomials with larger spectral gap and there are no codes associated to them. Or it could be that asymptotically the best possible spectral gap from polynomial will be exactly the same as from the codes. I don't think mathematicians know the answer to this. And that's to my surprise, because in Bootstrap case, which is more complicated, people know that spinless Bootstrap gives you solutions which are better than actual CFTs. Yeah, this is something, it's even in guys in your paper, there is a comment that it would be nice to go back to codes and redo this numerics. And somehow nobody did it, so maybe we should discuss it at lunch and see if that can be done. I don't know if that's a complete answer.
Yeah, a short question. It's applied, so I guess it's okay if you don't have the answer. But I understand that classical error correcting codes are essential for cell phone technology. Engineers have put a lot of effort to them. So how far are they from your conjecture?
Yeah. Well, I mean, they are conceptually very similar. For example, the sphere packing in 24 dimensions, which is famously used in Leech lattice. It's related to what is called Gallet code, and Gallet code has been used, I think, in a Voyager mission. It's a real space mission that people really use. It's a code which encodes messages in 24 bits or something like that. Now, when you go to very large C, people know much less. And of course, in telecommunication, in reality, nobody uses. Mathematicians love to talk about messages of asymptotically long length, because that's how you know the theoretical capability of your channel, right? Because if you want to optimize your channel in perpetuality, then you try to send messages of asymptotic length. But in telecommunication, as far as I understand, nobody tries to send messages which are asymptotically long. They chunk them in 24 or 18 or, 24 or 8 or 16. So conceptually, this is very, very similar, but in practice, this is slightly different things. Maybe a useful comment is that I'm not trying to improve code theory because I have no tools, but the idea was to use some knowledge from code theory. I don't think I can use knowledge from code theory to really propel knowledge about CFT, but at least we see that there is a very nice similarity, and the questions we are studying very similar questions. So if you manage to get a technique which improves one thing, you might be able to make progress in another as well. That's the best I can do.
So here you were talking about this gap in the U1.
Yeah.
So is that also an application of this code to standard gap in the protocol?
Yeah, we're coming to conclusions. Can we go beyond the Ryan theories? I really hope we do. Obviously, when you talk about additive codes, that's like a linear structure. There is a lattice behind it, so that's probably related to Ryan CFTs. But especially with the top-down construction, where codes have some physical meaning in the Hilbert space, I harbor a hope that there is a way to relate more general CFTs to codes. But honestly, this is a completely open thing. We might be close to a proposal what kind of code is dual to or related to Eisen CFT, but that's because of some algebraic peculiarities of Eisen CFT. We don't have any proposal for a general two-dimensional CFT what code would be. Once we overcome that super important step, then of course we can start talking about spectral gaps of non-Ryan. That's exactly where I wish this whole thing would be going, but I think it's a difficult direction.
In effective field theory, if you have a Planck scale, it seems to be, if you don't have any symmetries enforcing it, we think it's hard to put states well below the Planck scale.
Mm-hmm.
Is there a relationship?
Could you, what is exactly?
Well, the hierarchy problem is sort of reminiscent of this idea that most codes have a large gap.
Yeah, okay, so I have a comment. I do not know if that addresses your thing, but it's a very useful thing at the level of philosophy. So the only CFTs we know explicitly are small spectral gap CFTs, so you can even wonder, are there holographic CFTs at all and how many of them? But if you think that averaging over all CFTs gives you holography, like you were trying to explain to us earlier today, then it looks paradoxical. And that Slava, I think, and some other people like Amikas, they were like very skeptical. How is that possible? We don't know even one holographic CFT. So codes here give a very nice test bed, sort of understand what's going on. If we try to create a code from the first principles by writing it from symmetries, you will fail. And the code will have horrible Hamming distance, which doesn't scale linearly with the code size. But if you average over all codes, you will have Gilbert-Verschammung, which means that which is a Hamming distance which grows linearly with the code size. So mathematically with codes, and there's exponentially many of them, but finite number of them, we understand very clearly that a random code is a good code, is a large spectral gap. But once you try to do it from the first principles of a piece of paper, you will fail, because they're very, very, well, don't want to speak about Aeon in particular, but mathematicians systematically fail. If you write an explicit construction which has Hamming distance scaling linearly with the code size, that's a big achievement, and they write a paper about it. And I do not know if all, but most constructions like that use randomness. They say, oh, we now average, you take random this hits, and now it goes automatically. But if you try to do it from the first principles, you fail, fail, fail. So it's very similar to CFTs. You try to solve CFT, you fail. But there's presumably exponentially more CFTs which have speculation. Does that make sense? Okay.
Okay, no further questions. Let's,